Hello, it's Keith here, and this is lesson 4 of the TMS9900 assembly programming tutorials. Now, we know from the previous lessons that TMS9900 is a bit odd because unlike other processors, it doesn't have a stack. Now, today we're going to finally learn how it copes without that stack. Of course, it is with the concept of workspaces. We're going to learn what they are, how we can use them, and things like that. We're also going to look at some other commands with regards to working with the workspace register and also the status register. And finally, we're going to be doing the clever maths that the TMS9900 can do, the multiplication and division. So we're going to get into those things today and we're going to really learn about them. Okay, let's go over to the code and let's check it out. Okay. So workspaces then, well, what are they? Maybe you remember, maybe you don't, but we said at the start, a workspace is an area of 32 bytes that handles the 16 workspace registers that are very much like the 0 page of a system like the 6502. Now, when we call a subroutine, normally our return address will be moved into one of those registers and then we will return back to that return address later. And that's how we would normally deal with things. On a more common processor, of course, that return address would be pushed onto the stack, but TMS9900 has no stack, so that's not an option. So what happens is it goes into that other register. Now, of course, if we need that subroutine to use some of the registers, but we need those registers to be restored when we return back, with no stack we're going to have a bit of a problem. And this is where the workspace registers come in, because of course, being as they're just a bank of memory of 32 bytes in memory, we can use a different bank of 32 bytes for a new set of workspace registers for that subroutine. The little subroutine can do whatever it wants with those registers, and then it can return back to that calling subroutine, and the calling subroutine will still have all of its original registers intact. And of course, this can help with nesting, because unlike before when that link register couldn't get overwritten, well, now it doesn't matter if the link register gets overwritten within the subroutine, because when it returns back, the original link register will still be in the same state. So we could have nested subroutines, each with a separate workspace in memory, and as long as the same workspace isn't used twice by the nested subroutines, one parent subroutine having its data overwritten by a child, for example, then everything will work fine. So that's what we do, and that's how with my tutorial code I do things like the monitor. The current registers are all backed up into a separate workspace, and the monitor runs with its own dedicated workspace. So we're going to learn how to do that today, and that will really sort of fill in a big piece of the puzzle with regards to how the TMS9900 processor works, and one of the things that are very different about it, which I find especially fascinating when it comes to other processors. Okay, so let's fire up today's example and let's see what happens. So we're going to be doing workspace test 1 here first. Let's press 2 here to skip past all of that. And here is our output here. Okay, it's a bit complicated, there's rather a lot of it. So let's have a look what's actually been going on here and we'll figure it all out. Okay, so we're doing a show RAM here and we're showing the area 83A0 here. And you can see it's all full of zeros here. Now what we've done next is we've used branch and link with workspace pointer to this workspace pointer test here, this area here. Now this has two words in it. The first one is something called WSP test, which is pointing to the value 83A0, unsurprisingly the same area of memory we're showing just here. Now this defines the new workspace, and this is replacing the workspace register. You can see it just here, that's now been replaced, and that changes the source data position in memory of all of the other workspace registers that you can see being displayed just here. So these were the original ones here, and these were at the memory address 83C0, but now we've changed to 83A0, and we've got this alternate set just here, and you can see things like RB is now no longer initialized, it's now just defaulting to 0, same with RA here. But you can see also our other registers have different values here down here, and we will look at why that is in just a moment. Okay, so when we use the branch and link to workspace pointer here, we use the @ symbol to define the address that we're using, but the address isn't actually the code that we're going to run itself. It's two vectors, the first being the workspace address in memory to use for the new workspace registers, and the second being the actual jump to the code that we're going to run. And one practical use for this is if we do need to nest use of the same subroutine, we can use different definitions each time and the same code at the end. So for example, we could have 3 different versions of this like this. We could have branch and link workspace 1 and branch and link workspace 2, and the first one could use this address here, and then the second one could use something like that. Now, these would both work just fine, but they would be using different workspaces. So if we had a nesting where the same routine was being run at two different points within the same set of subroutines, then the child one using 8380 wouldn't overwrite the workspace registers of the parent one, which was using 8380, for example. So if we need to do quite complex things like that, that's one way we can get around it and allow the same piece of code to be run using two different workspaces. Now, in reality, that's going to be a little bit tricky on the Tmi99, because the Tmi99 only has 256 bytes of usable RAM, normal RAM. It's got video RAM, 16K of it, but actual normal conventional memory that the processor can access only got 256 bytes. So we're always going to be in this 8300 to 83FF range, and we're going to have to be a little bit sparse with our usage. Now anyway, so that's what this does here, and what you can see we actually did here is we started off our code here, we ran this subroutine just here, and we loaded in 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, and 4, 5, 6, 7 into the registers 0, 1, 2, and 3 here. You can see those values just here. Now, why we did that? Well, when we returned here, we then showed the RAM we showed before, the 8380 range, this range here, and you can see it now contains the contents of those registers, which shouldn't be too unsurprising, because when we set those registers, the workspace pointer was pointing to 8380, this memory area here. So this memory area here has worked as our registers within the subroutine just here. Now, of course, when we return, the workspace pointer has returned back to its original state, and that means that we're no longer using these. So when the show RAM subroutine worked, it didn't have any negative effect on the contents of this area just here. Now, one other thing I will show you, if I just rem this out here, and if I put another monitor in, I'm just having to do this because of lack of screen space, unfortunately. Well, now if I run a second monitor command after the subroutine, well, you can see here that the registers do contain the same values as they did originally, even though the subroutine changed them just here. And that hopefully will make perfect sense, because this was using workspace 8380, this test area here, whereas this one, and of course originally here, was using 83CO, which was unchanged by that subroutine. And that's the whole point. The subroutine does not change the registers, so that means that we can have our subroutine do its little bit of work, and then the parent routine gets on and carries on as if nothing has happened to its registers, which is what we want in this case. Okay, now, so the workspace registers are backed up and restored by this subroutine, the blwp command, but some of them do have special purposes. You can see registers 15, 14 and 13 here have acquired some new values here. Well, what are these new values? Well, let's have a look at that now. Well, the branch and link workspace pointer command itself actually uses these registers to store the other main registers of the system. What do I mean by the main registers? Well, these ones just here. You've got workspace pointer, program counter, and the status registers just here. And you'll see here that the workspace pointer was 83CO, and that's been transferred to RD here. This is R13. And then the program counter was 6040. Now it changed very slightly, but the new value was stored in RE here. And the status register, ST, was 9000, and that's been stored in RF here. That's R15, register 15. So these top three registers are actually still being used. Now, if we just go back to my tutorial documentation here, at the very start of these tutorials, we did discuss the initial register purposes. And you can see here that I did mark registers 13, 14, and 15 as being used in this sort of context when we were using the subroutine commands here. And R11 is the return address. R12 has another special purpose of its own, which is something called CRU addressing, which we're not going to cover at this time, but we'll probably get to at some point. It's relating to special hardware. Of course, if you're not using subroutines, then you can use these in whatever way you want. But if you are using a subroutine and you mess with these, it's going to break the continued functionality if you try and return. Okay, so I just wanted to point that out at this stage then. Now, once we've done our subroutine, we want to return, and we can't just use a jump that we would normally use, jumping to register 11 or register 10 if we've moved it around. We use RTWP, which is return and restore workspace, and that does all of the work of undoing the blwp command, and that allows our example code to carry on just fine. Now that's really all there is to it. It is a bit tricky. You've got to set up the vector correctly here, and for me at least, it was a bit of an alien concept, so it did take a little bit of getting used to. But I think if you create a few samples like this and just have a play with it, you'll be able to get the hang of it. And of course, we can do a subroutine within here, as you can see we've actually done just here. Now this is running a completely different subroutine as is this one. And if you look here, you'll see do next line W is actually got its own vector list here. It's using a different workspace again. This one's defined as WSP monitor, which will be a different area of RAM from this one. I think it's 8300 actually. I'm not quite sure, but it just doesn't matter what it is. It just matters that it's not the same one as being used by the other code. So that's how we can use multiple workspaces, and we can nest them as long as we're using different areas of memory each time. Okay. So that's the first thing I wanted to discuss. The second one is we're going to just look at some commands that haven't really come up yet, but now I think is the time to actually go over them. And these are the commands for initially setting a workspace and also for transferring the workspace register and the status register to another register. So we've got LWPI, which will load the workspace pointer from an immediate. Here we've loaded it from WSP test. And that, of course, is 83A0 here. So we've done that, and you can see that has indeed happened just here. It's been changed from 83CO to 83AO. We can also store the workspace register into another register, and you can see we've done that. We've transferred it to R0 here, and we can store the status register into R2 here, and you can see that has happened just here. And this is quite handy for my debugging when I need to show the status register to the screen visually and things. I do this. Now, these are the only commands available to us with regards to storing and changing workspace and status registers. But if we want to do more, we can always use a subroutine and then use the workspace area itself. And that's how I've actually shown the contents of registers. Like in this case, I loaded in the original workspace pointer, and then I loaded in from that area of memory and used that to show the contents of the registers to the screen that the original subroutine had, not the subroutine's own workspace. So as I say, I just needed to discuss these at this point. Now, of course, you will see there will be an LWPI at some point in our code for the initial example code. We do have to have some kind of starting value, and you can see it's actually being loaded in here, and its WSP default is 83CO. It looks like WSP monitor was 83EO. I couldn't remember that, but I say each one just needs to have its own. It doesn't really matter what they are. And you can see here we've started off by loading that as the default workspace. If we didn't do that, our code probably wouldn't work very well. Okay. So that's the second example we're going to look at. And then the final one is we're going to look at multiplication and division. Now, multiplication and division on the TMS9900 are pretty impressive, really. We're actually working at 32 bits here, using 2 consecutive registers. So in this example, we're going to use R2 as the destination, and that effectively implies that combination of R2 and R3 become the pair of registers that will store the result, with R2 being the top half and R3 being the bottom half. Now, the 2 parameters that are multiplied are R0 and R2 here, and so you can see the effective result of this calculation command MPY here is R2.R3 equals R0 times R2. Now in the case here, we've loaded R2 with the value FE32. We've loaded R0 with the value hexadecimal 100 here. Now we've loaded R1 and R3 with some dummy values here just to mark them and make it clear what their starting values were, just so we can see they change. Now we've taken FE32 and we've multiplied by 100 here, and that has of course moved it along, and that has sort of made it flow out of the first register R3 into the second one. So the FE part has moved to here, the 32 part is here, and you can see that this part is the 32-bit result of R0 and R2 being multiplied. Of course, I can just confirm that if we try some different values here. As I said before, I always encourage you to download and try different values. That's the point of me giving you the source code. So in this case, you can see here that it still spreads out into the second register. And if we just do a super stupid one here and we just multiply by 1, for example, well, now even though we didn't need the 2 registers, the second one of course does get cleared anyway, so the result is always 32 bits here. Now, as well as multiplication, we can also do division. Now again, this is 32 bits, so in this case we're going to use the 32-bit pair R2 and R3, and we're going to divide them by R0 here. And so let's just see this one in action. So we're going to divide R2 and R3 by R0 here. R2 and R3 create this big number FEDCB here. You can see it just here, FEDCB. And we're going to divide that by hexadecimal 100. The result will be in R2 and the remainder will be in R3. So in this case, we've taken this long number here, we've divided by 100, so it's moved 2 digits to the right, so it's become 0 FED, but the remainder is CB here. So this part was undivisible. Now, of course, we can just do a different value here just to sort of see that a bit more clearly. So this time we've used different values here. So the remainder was just B, and you can see now the whole of this value is just here. Now, of course, there is a risk with doing this that the result will not actually fit properly. Now, in this case, we've tried to divide by 2 here, but the result is actually too big for a 16-bit register, so you can see nothing has actually happened at all here. We've overflowed here because, as I say, the register couldn't take the resulting value. So we do need to just make sure that our mathematics is going to be possible. Now, finally, let's just do a much simpler example that's going to be sort of more familiar for basic mathematics. Let's try the values 2 and 7 here. So, of course, if we divide 2 by 7, we're going to get a value of 3 remainder 1 here. And you can see that just here, R2 has got the whole number result just here, and the remainder is just here in R3 here. So you can see here that we do have the multiply and the divide options, although we are going to need to use a 32-bit pair as part of these commands. But as I say, very impressive, and coming back from the sort of 8-bit processors like the 6502 and the Z80, which were around at the same time, this is very impressive and really does, I guess, show its foundations in being a server processor. It does really have some commands that most desktop processors wouldn't have had at the time. And again, you know, that 32-bit functionality there, really something you wouldn't necessarily expect from a processor that was aimed at sort of a relatively low cost desktop computer. So there we go. So that's the end of this lesson. We've covered some more of the important parts of this processor. I hope you found this interesting. I personally find the Workspaces very enjoyable. It's something really quite remarkable about this processor, and it's something that attracted me to it. So I hope you've enjoyed this video. If you have, please like and subscribe. If you like the videos, YouTube will recommend them to other people, hopefully, and maybe more people will find them and enjoy them as well. But whatever you do, I hope you enjoy the Ti-99, and I wish you all the best with whatever creative projects you're doing. Thanks for watching today, and goodbye.